welcome to this very special lecture. This is the 30th anniversary of the holiday lecture, and it is really my privilege to share this special occasion with you today. I promise you a good time, and you'll enjoy what we're going to share with you today, especially if you pay close attention. This being the 30th anniversary of the holiday lecture, we normally mark 30th anniversaries by using pearls. But in chemistry, we're going to mark this anniversary by using element number 30. That's zinc. Zinc is element number 30 in the periodic table. And zinc is a substance that is common in our daily lives. We have many examples. This adjustable elbow, for example, is galvanized iron. It means it has zinc in it. We have zinc products. We have zinc products in body care, health products. We have them as dietary supplements. And the food that we eat, meat, for example, has zinc in it. We're going to learn not only about zinc today, but about a lot of other different types of chemicals. And the first experiment we're going to do is to let the genie out of this bottle. This bottle has a genie in it, and I want you to notice the size of the bottle as I open the cap and let the genie out. You like that? I also want you to notice what's happening to the size of the bottle. The bottle is shrinking. That's because the heat that's released from this reaction that caused the genie to come out partially melted the plastic from which the bottle is made, and it has shrunk. Now I'm going to do another experiment with a very common household item. You recognize what this is. What is this? A cup. What kind of cup is it? A styrofoam cup. Yes, indeed. And what do we usually put in cups? We put something that we drink, or we put liquids in cups, right? So what I'm going to do is take a liquid out of this bottle. It's a clear and colorless liquid. I'm going to put it in the cup and oops, the bottom fell out. So it looks like this liquid, which is called acetone. You have acetone around the house. Where do you have acetone? Nail polish removers has acetone in it, right? And it looks like the acetone is dissolving the styrofoam. Actually, what's happening is that the acetone is taking the foam out of styrofoam, and what we're left with is the very same polystyrene, which is a polymer that was made into a rigid foam initially. We have also these packing peanuts that are also made of styrofoam. So let's put them in here. Try to get them all in there. Oh, I missed a few here, but that's all right. I can catch them in there like so. And try now to see what I'm seeing. The foam is collapsing. It looks like it's dissolving, but it isn't. It's still down there. All right, so at this time, I would like you to join me in welcoming a person that has been not only a collaborator, but a friend for the past 20 years, and that is Dr. Rodney Schreiner. Please welcome Rod Schreiner. Hello, Rod.
Dr. Sam.
Happy to see you.
In honor of your 30th anniversary, I've brought you a piece of element number 30.
Element number 30.
A piece of zinc.
A zinc strip. Well, thank you, Rod.
Yes.
I will cherish
You're
this.
welcome.
Yes.
You're welcome. Don't go too far away with that.
Oh, you need this.
Oh, yes. We're going to do some experiments with that because I want to show everyone that zinc is one of the more reactive metals. And because it is, it's used in all sorts of products. One important use is in this.
Batteries.
Which is a battery, right.
Yes.
Right. There are all sorts of things in our everyday life that operate on batteries, and many of those batteries have zinc in them. Zinc in this form, the gray metal. One of these electrical devices I'm sure all of us have seen is the electric wall clock. This one is perhaps a little different from ones you've seen. This one doesn't have any numerals on it. Instead, it's got the symbols of elements. And the elements are in the location of their number. Element number 1 is hydrogen. Element number 2 is helium. Element number 3 is lithium, and so forth. course, zinc, being element number 30, would never end up on the clock. But it's behind the clock. It's in this battery, and if I remove the battery, what happens to the clock? The clock stops. But I'm going to try to use this piece of zinc to get the battery or the clock running again. So first, I'll make some electrical connections to where the battery was located. Find those little contacts back here. Then I'm going to take the zinc and place it into this colorless solution. The solution also contains zinc that's been dissolved. Then I'm going to take a piece of metal which is zinc's next door neighbor. It's element number 29, and that's copper, and place it in this blue solution. The blue solution contains some copper that's been dissolved. Then I'm going to connect the two solutions with a little tube that's got some jello essentially in it, so that there is a wet connection between the two. Then I'm going to connect one of the wires to the piece of copper. If I can get the clip open. There we go. And I'll connect the other wire to the zinc metal. And what happens? The clock runs.
Thank you, Rod. So in this experiment, we've changed what? Chemical energy into?
Right. We're taking the chemical energy from the reactive zinc and transforming it into electrical energy, which drives the clock, which is exactly the same thing that happens in everyday ordinary batteries.
So I get to keep this battery now.
That battery you can have.
I'll use it for something else. All right. Thank you.
Okay.
Thank you.
I'd like to show you some other reactions of zinc, which are going to take place here. In this apparatus, which has a large glass globe and a tube below the globe, inside the tube here at the bottom is a mixture of powdered zinc and another element, iodine. Zinc reacts with iodine, but when they're together here, they're not reacting very quickly. Zinc reacts with iodine the same way that iron reacts with oxygen in the air. And you know, when iron reacts with oxygen, it forms rust. That happens much more quickly when the iron is wet. This reaction between zinc and iodine happens much more quickly when it's wet. So I'm going to put some water in there with it. I'll take the globe off, hand it to Bassam.
Thank you.
Remove the stopper and pour water into the tube. After I've poured the water in, I'm going to ask Bassam to place the flask back in position.
Right now?
Now.
All right. Just like that.
Just like that. Just in time, too, because look what's happening here. The zinc is reacting with the iodine, and that's making the mixture hot, and iodine vaporizes when it's hot. We are looking at iodine vapor. What color is iodine vapor? Yes, exactly. We have a purple vapor of iodine.
Very nice. Very nice. Thank you, Rod. Thank you.
Now, I saw earlier you were working with liquid nitrogen. Do you have any of that liquid nitrogen left?
Yeah, I think I might have some. Let me just check here.
I'd like to use some of that liquid nitrogen to cook something.
Actually, I have a lot here.
Okay, well, there's the liquid nitrogen. And I've got my ingredients, the other ingredients right here. My kitchen utensils, and the other ingredients are cream. Got lots of cream here. I'm going to ask you to help me to assemble this.
All right.
Lots of cream, flavorings, and sugar.
All right.
So why don't we start by pouring the cream into the pan.
Put the cream into the pan.
Put the cream into the pan.
All right. All of it?
All of it.
All right.
Pour it in. Okay. That's
some more?
Some more. Right.
This is very rich cream, Rod.
Only the finest ingredients. Okay. Now, of course, cream is very high in fat, and I know some of us are worried about our fat intake, so I'm going to dilute it a bit with some half and half. There we go. Major ingredients are in. I like things sweet. Let's add a bit of sugar. You've got the sugar there. I'll stir it in.
I have sugar here.
Okay.
Yeah, sure.
Okay, add about half of that.
Half of what I have in here?
Yes.
All right.
So I'll mix it.
So you're mixing the sugar with the cream.
That's right. I'm stirring it up so that
Okay.
the sugar is well mixed.
Is that about enough?
Well, you know, the more sugar you put in, the sweeter it'll be.
Oh, wow.
Well, I think we've got enough sugar now.
All right.
Okay, well, we'll want a little flavor, too, a little additional flavor. Okay. I have some vanilla. I'm very fond of vanilla, so put a lot of vanilla in.
A lot of vanilla?
A lot of vanilla.
All right.
Oh, keep going.
Keep going. More?
Okay, that looks good.
That's good?
That looks good, yes. Then I think we'll add some more flavor, too. Some fruit flavor would be nice. Let's try that preserve.
Oh, yes.
And here's a spoon to help you get it out.
So let's see, how much should I put in there? Just
What is this?
1 spoonful, or it's strawberry. Oh, it's actually
Oh, it's raspberry.
raspberry.
I like raspberries.
It's raspberry.
Let's use all of it.
all of it. All right, all of it.
Oh, this is really stirring. There, that's looking good. That's
So we're
looking
mixing
good.
all these different ingredients.
Right. Now we have all the ingredients in but one.
Which one is that?
The one I asked for at the beginning.
Oh, you mean the liquid nitrogen?
The liquid nitrogen.
Well, I've got that. I got plenty of that.
I'm going to switch to a spoon.
All right.
I'll keep stirring. You add liquid nitrogen
To this mixture.
to this.
All right. I'll do that. How much should I add?
Oh, I like liquid nitrogen. You can
All
put a
right.
lot in it. Keep going, keep going.
Keep going. More is better, right?
Oh, yes, yes. Now we're cooking. Now we're cooking.
It's cold there, Rod.
Keep pouring, keep pouring.
Minus 196 degrees Celsius.
Yeah, my hand's getting a little chilly, but you know, you have to suffer for. Oh, something's happening here.
Something is happening.
Something's happening here. You know, this is getting kind of stiff. It's getting stiff.
What have we made here?
Look at that.
Strawberry
What
or
have we
raspberry
made?
ice cream.
We've made raspberry ice cream.
My goodness. But Rod, this is minus 196 degrees Celsius. Surely we can't eat that.
Yeah, that's right. This is much, much too cold to eat. I think I'll take it back and put it in the freezer and let it warm up.
Thank you, Rod. The next person I would like you to welcome to my lab is the person that is well known in our community for the program that he puts on called The Wonders of Physics. Please welcome my friend, Professor Clint Sprott. Hi, Clint. Welcome to my lab again.
Now we're going to get down to brass tacks.
Oh, it brought me some brass tacks. Brass, of course, has zinc in it, zinc and copper.
That's right. You know, it's a special treat to share this 30th anniversary with you because you know it was exactly 16 years ago that I sat out in the audience here and saw you do one of these presentations for the first time, and that was the inspiration for the Wonders of Physics.
I'm glad that you did that, Clint, really. We're all very thankful for you. Thank you.
But you know, you have a sign here that says science is fun, and you've been doing mostly chemistry things here. Don't you think we should do some physics?
I think we should do lots of physics.
I see you have a bicycle wheel over there.
All right.
Did you know that there's a lot of physics in riding a bicycle? How many of you ride a bicycle? Well, here we have a bicycle wheel, except this is a little bit unusual because this bicycle wheel has concrete in it, so it's quite heavy. There's a lot of interesting things one can do with a heavy bicycle wheel. One interesting thing we can do is to stand up on a rotating platform like this. Well, not much is happening. In fact, I can't even make myself spin around very well, except if I take the bicycle wheel and spin it, it causes me to spin around. Now, if I take the bicycle wheel and turn it upside down, it makes me spin the other way. And I can make myself spin either direction by turning the bicycle wheel one way or the other. Now, that's an important principle of physics that we're not going to have time to discuss today, but I just want you to know that when you ride your bicycle, you're using lots of principles of physics. Now, you know, another thing you've all seen is an ice skater. How many have seen an ice skater go out and spin around on the ice with their arms out like this, and then the skater will bring the arms up over the head like that and go around really fast? Have you seen that? You have to be really good to do that. I can show you an illustration of that, except I'm going to do it with a couple of heavy weights in my hand. And I'm going to get up on the rotating platform and spin around a little bit, like this, with the weights out at arm's length. Now watch what happens when I bring the weights in close to my body. Whenever the weights are out, I go slow, and whenever the weights are in, I go fast. And that's just like the ice skater. When she takes her arms and brings them in over her head, she brings them in close to the axis of rotation, and that makes her go fast. Now, another thing we study in physics is electricity. And for the next demonstration, I will need a volunteer. Who would help me with this? Someone? Let's see. I need a special kind of person for this. How about you? Come on down here. Come right down here beside me. Turn around. What's your name? Molly. Molly? Molly, have you ever been out in a lightning storm? No. No? You've seen lightning though, right?
Yeah.
Through the window?
Yeah.
Yeah, well that's good, you know, because lightning can be dangerous. But we're not going to hurt you, Molly, but we would like to take you somewhere where there's a very high electrical voltage. You up for that? Okay, Molly, follow me right around here. And what I would like you to do is step up on this platform, face the audience, and put that hand right there. Now, this is what we call a Van de Graaff generator that makes about 100,000 volts. And whatever you do, Molly, whatever you do, don't move your hand until I tell you, okay? So I'm going to turn it on. It makes a little bit of noise. Molly, shake your head. Molly, don't you ever comb your hair? Look. Now watch your hair as I discharge it. Thank you, Molly.
Thank you very much, Professor Sprott, and thank you for being so inspiring, not only in physics, but in all of science. Thank you very much.
Well, thank you.
Thank you. Now I'd like you to welcome a person who's been in my lab for the past several years, and she has some experiments to share with us. Would you please welcome Elizabeth? Hi, Elizabeth.
Hello.
I noticed you're limping.
Yeah, I hurt my foot dancing.
Oh, I hope your foot gets better real soon.
Thank you. Well, I have for you today, in honor of your 30th anniversary, some calamine lotion, which, as you know, contains the ingredient zinc.
Another body care product that contains zinc. Yes, thank you. Thank you, Elizabeth.
And we also have this wind bag.
Whoa, that's colorful.
Yes, it is. Do you think you can inflate this?
This whole bag?
Yeah.
Oh, I bet it'll take me a long time to do it. Can you help by tying off the other end there, and I'll
Sure.
try to. So you just blow into it. Is that what you'd like me to do?
Yes.
All right. Got to keep the air in, right?
Right.
Do you have to keep doing this? I'm hyperventilating a little bit.
Here. Well, Professor, that's pretty good. But
Well-
I think I can do better.
You can do better than that.
I think I can do it in one breath.
Okay. Whoa. Do you think she can do it in one breath? She's very confident. Of course, she works in my lab, so she's got to be that way. All
Could you
right.
hold this end
Hold
for
this,
me?
all right?
What you forgot to do was to use Bernoulli's principle.
She did it. Now, what was that principle again? Bernoulli's principle.
Bernoulli's principle.
Now, people know about Bernoulli's principle from a lot of different experiences that we have in our daily lives. Sometimes you may have noticed that when you turn the shower on and the shower curtain moves inward in the same direction as the water flow, that's an illustration of Bernoulli's principle. And so that's very nice of you that you showed us how to do this, Elizabeth. Do you have something else in there?
Yes, I have this mug in honor of your 30th anniversary.
Oh, thank you. Is there something special about this mug other than that you're giving it to me?
Well, I was wondering, did you want to do some experiments with that mug?
Sure, I like to do experiments with it, yes.
Do you think that I can hold that mug up without using my hands?
You mean like put it on a table like this?
No, I mean suspend it in air.
Suspend it in air without holding it with your hands.
Yep.
Okay. You want to show us how to do that?
Well, could you hold it for me?
Oh, you want me to hold it? All right, I'll hold it. Okay. What are you going to do now?
I'm going to inflate this balloon in the mug.
Now what?
Let go.
Let go. You sure? Ta-da! Thank you very much, Elizabeth. I really appreciate your sharing these experiments with us, and you've done a good job both with the balloon and with this big wind bag. Thank you very much. I hope your foot gets better soon. All right, we're going to now do some more experiments with, what am I holding here? Am I holding the balloons? Where are the balloons? The balloons are up in the air. What's holding the balloons up in the air? Well, strings are holding the balloons up there, right? What do these balloons have in them? They could have helium. That's a gas lighter than air, right? And that's a gas also that does not burn. So if I were to put a flame to the balloon, then I will discover whether or not there is helium gas in there. There are other gases that are lighter than air that burn. And so one way to find out what's in the balloons is to put the flame to them. Here we go. Are you ready? All right. Well, that balloon didn't have helium in it. That balloon had hydrogen in it. Right? It had hydrogen in it, and that balloon, the hydrogen in that balloon combined with the oxygen from the air and caused that explosion to happen. So let's try this next balloon here. As some of you are covering your ears, why are you covering your ears? Because you learned that there's sound energy being released in addition to the light energy. So let's try this one and see. Oops. That sounded like a dud, right? That's because it had helium in it. Now, what we're going to do is try this third balloon, but I will tell you this third balloon has in it a mixture of hydrogen and oxygen. More oxygen in it than is in the air. And so I would like everyone to protect your ears from sound, potential sound damage by taking both fingers, sticking your fingers in the ear like this, okay? Well, I can't do that and do the experiment at the same time, so I brought with me some earplugs. So I'm going to put the earplugs on, and I want you to be protecting your ears. If you can hear the sound of my voice, that means you don't have your ears well protected. I can see that you're smiling because I can't hear you. So protect your ears very well as we now do our grand finale. Here we go. Thank you all very much for coming. Thank you very much. Thank you very much for joining us. Thank you. Thank you. Thank you very much. Thank you.